The Steel Structures Education Foundation is an organization established to foster increased awareness of steel as a building material and to expand the knowledge and understanding of the use of steel in construction. We are proud to present this steel construction story. This program is about multi-story steel frame buildings. Whether 2 stories or more than 100, they present common architectural and engineering challenges. We will address some aspects of planning, design, function, and construction. In Part 1, we examine the lateral loads which multi-story buildings experience and some fundamentals of design, including the vital communication between structural and architectural design. In Part 2, we show how steel framing supports the structure, with particular attention to floor framing systems and the integration of essential services. We will also see how the design comes together in actual construction. Multi-story buildings can expand the scope of suburban areas, or they can rejuvenate urban areas. Their size varies widely. Planners use the term density to describe building size. That is, the ratio of floor space above the ground in relation to the area of the building lot. Densities of 2 to 12 are common, and they can reach 25 or more. Zoning bylaws restrict densities and height and impose stringent rules to create open space and reduce encroachment on neighbors. Buildings built today require longer floor spans and new high-tech services. The first step in urban construction may be complete demolition of the existing buildings. However, there are other options. Floors may be added to an original structure. Due to the foresight of the builder or the heavy floor loads required by an earlier occupant, this building has reserved structural capacity required to support these 6 additional floors. In this case, the new construction encapsulates the original building inside its new skin. In the third instance, the original structure and its facade are maintained. The new architecture contrasts dramatically with the old. Whether modified or new, the structure must contend with the forces of man and nature. Nature's influence on multi-story buildings takes 3 primary forms: gravity, wind, and earthquake. Gravity or vertical loads are primarily due to the mass of the building, its furnishings, and occupants. The effect of building height on gravity loads is more or less linear. Wind loads multiply exponentially with an increase in building height. Earthquake or seismic loads vary depending on location and expected severity of an earthquake, based on our short-term historical knowledge. For this reason, over and above architectural constraints, the major consideration in developing a structural concept is the capacity to resist lateral forces. Wind loads on the walls are transferred to the structural frame through the structural framing and floor diaphragms. Since all building materials are elastic, these loads will cause a structure to deflect laterally in accordance with Hooke's law. Earthquakes have a similar effect, although forces are exerted on the building by movement of the Earth's crust. The building forms its own movement mode in response to the vertical and horizontal accelerations of its foundations. The designer's major concern in this case is the prevention of structural collapse under extreme loads. Structural steel buildings are renowned for their ability to withstand major earthquake shocks. The reduction in building mass because of steel's high strength-to-weight ratio reduces seismic forces on the building, and the ductility of a well-detailed frame allows it to resist many cycles of extreme load without failure. There are various lateral load resisting systems to be considered. The basic types encompass bracing, rigid frames, and shear walls. These systems act as vertical cantilevers, anchoring the building frame to the foundations. Their function is straightforward, but each is unique as demonstrated by their simplistic deflected shape. Let's consider first the steel-braced lateral load-resisting system. A single-story building frame demonstrates the function of bracing in its simplest form. The performance of each element is clear and simplistic. But as the building height increases, the loads and complexity of the system also increase, and the location of these essential structural elements takes on greater importance. Obviously, the design team of structural engineer and architect has to work closely together. Only in this way can they ensure that the lateral load-resisting system selected meets the needs of the structure and is compatible with the architectural concept. One fundamental difference between single-story and multi-story buildings is the need for a service core. It's usually centrally located and holds elevators, stairs, and washrooms, plus mechanical and electrical services. This core is also a logical location for the lateral load-resisting system. Now, let's add more floors. Careful proportioning of the brace frame members will be required to comply with the functional design and still meet the structural design criteria because the core will tend to be more slender. As buildings increase in height above 40 stories, a core system becomes less efficient. However, the braced core can be propped by adding one or more pairs of outriggers off the vertical bracing trusses. These stiff elements, attached partway up the core, transfer forces from the core to columns along the outer walls of the structure. This provides the maximum possible base width for the lateral load-resisting system and the maximum control of lateral deflections. Before we look at higher buildings, let's go back about a century. Gustav Eiffel faced these same structural challenges in the design and construction of the Eiffel Tower. It was built for the Paris Universal Exposition in 1889, and at 300 meters was, for many years, the tallest tower in the world. The basic structure and the lateral load-resisting system are one and the same. The tapered shape has two effects. First, it lowers wind loads as height increases because the surface area reduces. Second, it provides the wide base required to resist the large overturning wind moment. Let's explore this concept further and think of the tower as a vertical cantilever. The wind pressures Eiffel assumed on the cantilever created a shear force diagram, which looks like this. From the shear diagram, we can calculate the overturning moment diagram, which varies exponentially with height. Let's be unconventional for a moment and reshape the bending moment diagram to form a shape symmetrical about its vertical axis. Now, compare this shape with the shape of the tower, and we find a remarkable resemblance. Eiffel capitalized on the laws of nature. He shaped his tower to the wind bending moment to maximize its structural efficiency. Today, we face man-made forces in addition to nature's. If Eiffel had been faced with our building codes, zoning bylaws, density controls, and height limitations, his tower might have had quite a different shape. This 100-story structure, built 80 years after Eiffel's masterpiece, benefits to some extent from the same theory. The world-renowned designer, Dr. Fazlur Khan, found that by selecting this tapered shape and placing wind bracing on the exterior walls, there was no premium for height, no material added to control lateral deflections. Bracing members transfer forces across the face of the structure and around the corners, making the frame perform as a whole, more or less like a box or a tube, hence the term braced tube. Now we have seen diagonal bracing used from 1 to more than 100 stories, but what if we build without them? This involves an entirely new concept, the rigid frame. The rigid frame is formed by rigidly connecting columns or verticals to girders or horizontal members. Lateral forces are resisted by bending and then by axial loads in the columns. The rigid frames may be located on the perimeter frame of the building or throughout the entire structure. Rigid frames are often used where ductility is required for earthquake resistance. In shorter, rigidly framed buildings, girder lengths are usually 2 to 3 times the story height. As building heights increase, rigid frames with widely spaced columns become less effective because of the lack of girder stiffness. If columns are placed more closely together, girder length is reduced, stiffness is increased dramatically, and a framed wall is created. Stiff connections can be provided to transfer forces around the corners of the building frame, making the structure perform as a tube, logically known as a framed tube. This structure has the obvious characteristics of a framed tube, with a deep steel spandrel girder. Closely spaced columns breaking the span of the girders are somewhat disguised by the horizontal accentuation of the architecture. In a similar structure, the architecture has a dominant vertical accentuation. The deep spandrel girders that match column stiffness and create the tube effect remain hidden behind the glass facade. There is one more major lateral load-resisting system to consider, the shear wall. The obvious location of shear walls is in the building core. Methods of building the core can vary dramatically. In this example, steel shear walls resist lateral forces directly in shear and bending. Each wall consists of a thin steel plate with edges stiffened by columns to form what is, in essence, a deep beam, cantilevered off the foundations. Larger steel plate core walls have also been used. Frequently, shear walls in the core are concrete. These cores may be built ahead of the steel frame, with the steel frame, or behind it. Concrete cores built at the same level as the structural steel do not allow maximum efficiency of either core or frame construction, so we will not consider that method further. When steel frames are built ahead of the core walls, steel erection may proceed independently of other trades. Temporary steel columns, extra steel beams, and temporary bracing must be used to resist construction and wind loads on the frame. Infill shear walls are cast after steel erection. When the core precedes the steel frame, the vertical gap in construction avoids conflict between core construction, steel erection, and other trades which follow. In a core ahead project, an experienced contractor will accelerate core construction to a maximum because the steel frame will proceed at a faster rate and catch up. Ideally, the catch-up does not occur until the top of the building is reached. As we have seen, multi-story buildings indeed have many facets, including height, size, and shape. We have reviewed lateral loads and structural systems to resist these loads. When we continue with Part 2, we will explore some of these systems in action, along with various floor framing systems. And we will also explore the construction techniques used to erect steel-framed buildings. In the first part of this program, we reviewed basic multi-story concepts and lateral load-resisting systems. Now let's look at floor framing systems and steel frame fabrication and construction. Since floor framing systems represent a major component of multi-story building costs, they demand particular attention. The simplest and most conventional framing system is hot-rolled wide flange beams. This is the least expensive material, requiring a minimum of fabrication labor. Mechanical ducts may pass beneath the beams or through holes cut in the beam webs during fabrication. Trusses are an alternative framing method. Triangulated web members in one of several configurations join top and bottom chords together. Trusses are lightweight, efficient on long spans, and they provide ready-made openings for services. There are other advantages. Because each component may be sized for specific tensile or compressive loads, we can achieve considerable cost savings in spite of the increased labor for fabrication. We can capitalize on the standard concrete floor slab placed on steel beams or trusses by using steel as the tensile shear component and concrete as the compression component in flexural members. The resulting compositely designed members provide a more economical use of the structural steel. Although beams and trusses may be composite or non-composite, a third floor framing system, the stub girder system, must be compositely designed. This system was developed to minimize both structural steel content and building story height, and in this case, the concrete floor slab must be connected to the stub girders with shear studs, forming the top chord of a composite member. Since stub girders develop a substantial part of their strength from the concrete cover slab, they must be shored while the concrete is placed and cured. Beware of unnecessary expense for excessive shoring. A simple arrangement of shores is usually all that's necessary. Now let's look at columns. Because a column at each floor level supports less load than the story below, a different size could be used for each level. This concept is illustrated graphically with an exaggerated horizontal scale for clarity. However, columns are usually fabricated in 2- or 3-story tiers as a trade-off between steel material and labor. Longer segments minimize the number of shop splices, field splices, and crane lifts. The size of a column shaft is governed by the loads at the lowest story of that tier. The upper levels of a tier will be somewhat oversized, but using the same size member for 3 stories means that floor framing at all 3 levels will be the same length. This increases the number of identical pieces and reduces the number of shop drawings. It also cuts down on the risk of error or fit-up problems during construction. While we have been preoccupied with design, steel making continues as an ongoing process at the mill. The basic oxygen furnace feeds the continuous casting lines, producing dog bone shapes destined for wide flange beams, and slabs destined for the plate mill in anticipation of orders. When design is complete and a contract awarded, the next step is ordering the steel. Various quantities of sizes and shapes will be required. The steel fabricator prepares order bills for material and shop drawings for each component. These drawings provide precise dimensions and identify fabrication procedures. Beams and columns can be cut to length with a cold saw that leaves a square finish acceptable for many applications. Larger columns, both hot-rolled and those fabricated from plate, will normally have the ends milled for squareness. Once the materials have been cut to length, a computer-controlled beam line is used to drill holes for connections. Smaller pieces are sheared to size and holes are punched as required. Fitters and welders add the connections to the beams and girders for assembling the components into the building frame. Trusses are fabricated from pre-cut components and welded on an assembly line basis. Today's trend is to long spans, and provision must be made for the flatness of such long span floors. Trusses and beams designed to act compositely with concrete floors are light and slender. They will deflect under the weight of the concrete. To counteract this, an upward curvature called camber can be introduced to assure a flat floor after the concrete is placed. After the concrete is cured, the beam is very stiff and deflections are small under live loads. Beams may be cold cambered by bending with hydraulic jacks. In this operation, the steel exceeds its elastic limit and yields. But don't worry, the beam maintains its original strength. Trusses are treated in a similar fashion, but cambering is set up in the jigging operation so that a predetermined amount of curvature is fixed before welding. With fabrication complete, we begin erection. This building has a braced core to provide the lateral load resisting system in both directions. A team of iron workers, often called the raising gang, erects the core elements, the columns, the girders, and the diagonals forming the lateral load resisting system. The crane operator is directed by radio or hand signals as he places the steel where highly skilled iron workers, known as connectors, bolt the members in place. All framing is plumbed and leveled with precision surveying equipment and is held in place with plumbing cables until the bolting up crew and welders complete the connections. Exterior columns are next, followed by the primary framing members, which tie these columns together and tie them to the lateral load resisting system. Once all the secondary framing members are in place, the connections complete and the frame plumbed and squared, the steel floor deck is placed and fastened to all floor framing members. The deck serves as a working floor for iron workers, proceeding with the next tier of steel, and as a safety floor for workers above and below. Stud shear connectors can then be welded through the deck into the steel framing in areas where the floor framing members are compositely designed. The steel floor also performs an essential function as a structural diaphragm, holding the frame in vertical and horizontal alignment and tying the elements into the stabilizing core. Several levels may be built using this temporary system for stability. A concrete cover slab is placed on top of the steel deck to provide the finished building floor surface and to provide a stiffer, stronger structural diaphragm. This diaphragm is considered a structural element and is used to stabilize columns in the completed structure. Let's look at some of the techniques used to expedite structural steel erection. Single-piece lifts from ground to work level can occupy the crane for long periods while the hook travels up and down the building. This becomes more critical as structures reach higher. It's more economical to hoist bundles of steel to the work floor, where they can be placed quickly and efficiently using a light runner line on the crane jib. Sometimes framing members can be pre-assembled on the ground before being hoisted, saving valuable labor by connectors. This is particularly important at the exterior of a building, where exposure to falling is greatest. The crane is also tied up for less time. As soon as the steel assembly is temporarily connected, the crane hook can return for another lift. Multiple member lifts, slinging one above the other, are also frequently used on higher buildings. These may be hoisted from the ground or from a stockpile on the work floor. While each beam or truss of one lift is bolted in place, the rest of the crew prepares a new multiple lift, and erection proceeds bay by bay around the building. Every effort is made to avoid having the connector climb a column to unhook the crane with such devices as quick release hooks, but sometimes a little assistance is required. Next to their spud wrench, usually required for aligning bolt holes and temporary connections, the crane is the most important part of the erection gang's equipment. There are numerous kinds. In buildings up to 15 stories or more, a mobile crane can sit on the ground outside the building footprint. It will not apply any loads on the building, and construction can proceed without consideration of forces from crane operation. Stationary tower cranes outside the tower footprint can be used on taller buildings, but they must be tied to the frame for stability, which results in some lateral loads being applied to the building frame during crane operation. At the other end of the scale, this crane relies on the building frame for the support of all vertical, horizontal, and overturning forces. This is one of the world's most advanced cranes. The crane is jumped or hoisted up the tower as each tier of steel is completed. It takes only 15 minutes for the jump, and the crane is out of service for less than 2 hours. The first step is to release the secondary support on the crane tower. Support brackets are hydraulically retracted, and the entire support frame is winched up the tower, guided by rollers running up the corners of the core columns. Once this support frame is secured to the building frame, it becomes an anchor for the hoists, which lift the main support platform and the entire 150-ton crane 12 meters or more up the tower. It is then secured and back in operation. The building core design may determine the type of crane used. An all-steel building with a steel-braced core is the simplest. Only one trade is used, and the erection crew's efficiency is at a maximum. Other approaches are common. In this sequence, we can see a special core form system which uses hydraulic jacks to lift itself up the building, keeping the crane free for other duties. This is particularly important when core construction and steel erection are proceeding separately, as mentioned earlier. Now let's put it all together. This bold statement on the skyline was inserted between two landmark buildings. Inside the facade of stone and glass lies what appears to be a complex building structure. But a closer look reveals a framework of simple elements connected together to create a large clear-span floor area. Construction began with a bus terminal, a parking garage, and other service areas built 5 stories below street level. Once the decision to build is made, the completion date usually becomes critical. The sooner the better. This alternative design-build steel proposal proved to be a winner. The Building Service Corps precedes the framing to provide stability during construction. Steel erection follows quickly, and a few months after the foundations began, the frame is topped off. The construction schedule at this point matched a neighboring building of the same height, which started about 12 months earlier. A technique sometimes considered to expedite construction of multi-story buildings is to start by erecting freestanding columns from footings to ground level in single lifts 3 to 5 stories high. Using this technique, the tops of the columns are framed in by beams, girders, and deck at ground level, creating a diaphragm to stabilize the columns and to form the base for the tower columns above. Construction then proceeds upward, while the more complex and time-consuming structure below ground level can be built at its own pace, off the critical path. Earlier we discussed revitalizing the inner city by adding area to an existing building. Let's look at the stock exchange as an example. To make this project viable for redevelopment, its density had to be increased. The method chosen was to add rental space above and around the original landmark structure. We can see graphically how this was achieved. Since the existing structure could not support the 25 floors added to the project, a new structure was built around and above it. New columns support 4 massive transfer trusses weighing 200 tons apiece, which in turn support upper-level columns above the original roof. These trusses were too large and heavy to lift or ship, so they were stick-built piece by piece. Precision fabrication and erection were required to prepare the truss joints for hundreds of hours of field welding. Hangers were added to support loads below the trusses, and columns were set on top to support the floors above. The last beam was signed and hoisted into place for the traditional topping-off ceremony. Column transfers are often necessary in new construction as well. Note this large transfer supporting 20 stories, but also note the opportunity lost in this situation, where the owner may have been unwisely advised to reject this framing scheme and used this alternative, with a significant loss of prime executive office rental area on the building perimeter. Well-designed structural transfers can provide functional designs and maximize rentable area. For example, this massive transfer truss and this girder were fabricated off-site, trucked to the site, and erected just like more conventional girders. The difference is that this girder permits 2 tower columns supporting more than 30 floors to be terminated at the 5th floor, avoiding interference with a bus entrance below grade and providing a large open area in the lobby. Although this massive girder transfers more than 30 stories of load, this concept is often used in much smaller buildings, but is usually hidden by the architecture, transparent to the tenant, because of steel's ability to carry high shear forces in shallow members. Note the architectural setback achieved in this structure using a simple transfer every 2 levels. The term multi-story tends to make us think of skyscrapers, but as we have seen, a multi-story building can have as few as 2 stories. In buildings of any height, steel framing is a part of effective and efficient architectural and structural design, withstanding the forces of man and nature, and meeting the needs of owners today and in the future.